For a certain value or a specific value, remember there was someone who invented telephones named Graham Bell. You must have heard of him. Graham Bell is the one I refer to as Bell. You find that we took this unit, or that we are talking about ultrasound and its uses, and this unit expresses the amount of attenuation that occurs in the beam or ultrasound beam during its path, or attenuation that happens while the ultrasound bolt passes through. So it tells you here what the Biot-C-Bell expresses what exactly. It's like you're showing what these are, that I took it from you, and it comes out on a certain surface. This surface causes a part that I named and a part that experienced an incident on this surface, which I called I or I incident ratio. The ratio between the reflected intensity and the incident intensity is calculated using 10 to log, meaning through this equation, it gives you the amount of attenuation that occurred. The amount of attenuation that occurred means that through this, it gives you the amount that happened. You are calculating a ratio between two things, and this equation gives you how much has occurred. This is a fundamental concept in mathematics and physics, where ratios are used to compare quantities. The equation is a mathematical representation that helps in understanding the relationship between these quantities. So, how is this measured? Well, measurement is crucial in determining the exact value of the ratio, and it is done using precise instruments. It tells you that it approximately corresponds to the beam. The beam intensity means that if the beam intensity was 100% and it has now decreased slightly to 99%, then the beam has lost a certain amount in dB from its original intensity. If it has lost 22% of its initial value, then how many dB is that? The whole idea is that it expresses precisely the amount of loss in terms of intensity, or specifically speaking, the amount of attenuation which has occurred with a value called dB. To make it easier for you personally to start knowing exactly how much both reflected and incident intensities have been reduced significantly. This gives an established standard measure regarding precisely quantifying this attenuation concerning any signal whatsoever. So, how does this help me? When he knows accurately just how much exactly indeed the signal which came directly towards him initially has lost in terms of decibels, dB. What does all these benefits entail practically speaking? If I know clearly just exactly by what margin measured explicitly through decibels, dBs, the reflected signal itself actually experienced losses originally intended, then ultimately what happens next logically follows naturally. Okay, now let us consider another question. Does every ultrasound image? The image is usually bright from above, while the part below is completely dark. When I think about it, I say to myself, I'm sending a signal, and as it moves or as it travels through the patient's body, it weakens. So, the reflected intensity coming from a higher depth should be much weaker than that coming from the upper surface, right? The signal that is reflected on the transducer from the surface close to the transducer will be strong because the incident intensity was strong and hasn't experienced attenuation yet. Okay, the signal I'm receiving from higher depths has become weak. So, what do I want to do? I want to make the entire ultrasound image uniform. Therefore, I will perform an evaluation or estimation of the attenuation that occurred. I will check how much I sent and how much signal I received. Then, I want to know how many dB to compensate for the dBs we are referring to and add them to the received signal. So it says, what does it say? It says signal, or it mentions the signal that reached it, and you get a completely homogeneous image. Now, simply put, they said, Here is the example. Let's assume I have, for instance, different variables. Let's assume that this antenna is 100. All that is reflected here, let's say it's 20. So how much did it pass, doctor? 80, right? 80 here was 100. And it passed 80. Okay, so this 20 came from this distance. But on the way back, it also experiences attenuation. Now the signal coming from the other service. You will walk a greater distance, which will cause another attenuation. The original antenna here is 80. What comes to this service is that you will have two signals, one coming from service 1 and one coming from service 2. The signal from service 1 is strong, while the one from service 2 is weak because it comes from a higher depth. Now, as a transducer, if I take this signal as it is, you will find that the upper part, the first signal coming to you, is good and homogeneous, meaning it is illuminated, while the signal coming from below is dark because it is weak. You have experienced attenuation. What will it do? I know. No. The countries start to develop a new type of honeycomb for connection. For example, if you lost 5 decibels, you would add 5 decibels to the incoming signal, meaning you are compensating for the existing signal. No. Don't do that, doctor, please. Okay? Do you have something in the ultrasound? There are buttons arranged according to depth, or are they arranged in another way? It's the same concept. The same concept. To make everything homogeneous, all is one. What is the same idea? When you come to change, you use TGC. What do? You tell the service not to do it, or for the signal, and come to the processing. How does it actually do this? It does this by what I am saying. I mean, it's the same idea. It has a meaning, as you can see. When it perceives the signal, it performs amplification. Depending on the time gain compensation, TGC, you set. If you change the TGC so the upper part receives amplification, will the image differ or not? No, it's done. He sent what he sent. This is the incident, and he doesn't play with it. When he receives it, since it comes at a different time, coming from a far depth, he knows according to this time that it comes from a distant depth and with a weak signal. So he calculates the decibel level and compensates it according to the value you have set. Right, doctor? Mashallah, the clock shows 1:15. I am indeed ready. I am absolutely all set. There is no problem. Are you with me? Or did you disconnect? Okay, let me just give you a little something about what is happening. We will also continue with it next time. Just 10 minutes so we can wake up in the morning and stuff. Okay, a few more. There is a part that experiences reflection and another part that experiences refraction, and there is also a part that experiences scattering. All these interactions mean that we previously mentioned that the topic of frequencies, or the ultrasound pulse itself, is energy. This energy is transferred through the movement of molecules. When you provide energy to the molecules, it is very natural to have a loss in energy. This energy loss can occur in the form of heat. This loss means that the energy here is attenuated. For example, if the output interest is 100 watts, it might drop to 50 or 40 watts when it reaches a certain depth. This is because energy has been lost due to collisions or as a result of the movement of these particles, leading to attenuation. So, the transfer of energy occurs in the form of heat, resulting in loss. There is a type of this attenuation, or what is called absorption, that occurs. If I have a transducer here, and it emits a certain pulse, and for example, there is a surface here that is soft tissue, and I also have muscle tissue. Then we have two different materials, or two different tissues present. Each of them has something called impedance, which is the acoustic impedance. This acoustic impedance indicates whether the pulse will travel through easily, or if there will be an obstruction, similar to resistance in transfer or transmission, or the movement of the pulse. If the pulse is moving between two media that have different acoustic impedances, reflection occurs. In this case, reflection happens at the surface between them. The strength of this reflection depends on the difference in impedance between the two tissues present. The greater the impedance difference, the greater the reflection intensity. Similar to what happens in a regular echo. Impedance is defined as density multiplied by the speed of sound, meaning it depends on the density and the speed of sound within that material. The reflection that occurs depends on the difference in acoustic impedance between two materials, plus the square of the impedance of the second material, divided by the sum of the square of the impedance of the second material and the square of the impedance of the first material. The highest impedance is found in bone, while the lowest impedance is found in gas. If you were to be dishonest, this is the instant between, for example, if there is a part that undergoes transmission and a part that undergoes reflection. Okay? If I have these mediums, one is the liver and the other is the kidney, the reflection will be at 0.6 for the kidney and at 0.3 for the kidney, or 0.9 for the liver. Now the highest reflection is 59% of your beam will undergo reflection between the liver and the bone, soft tissue and bone. And you see that 99% of the beam will undergo reflection between the soft tissue and air. Why? Because there is a significant difference in impedance between them, and there is also a significant difference in impedance between soft tissue and bone. Therefore, this impedance mismatch is what causes a large part of the reflection to occur. A large part of the reflection occurs between soft tissue and bone. These are the highest values, along with soft tissue and air. Okay, if the beam or your pulse comes at a certain angle, which I call the incident angle, it will equal the reflection angle. The angle of incidence equals the angle of reflection for me, which is this angle. And this angle, good. If we discuss in detail now about acoustic impedance, and essentially the difference in acoustic impedance that indicates the reflection that occurs, well, for soft tissue and air, as well as soft tissue and bone, along with bone and air interfaces, it tells you that total reflection occurs at these interfaces. Why? Because there is indeed the highest difference in impedance present. Before we get into more details on this topic specifically, what does an ultrasound image look like exactly, doctor? Here you will find the best part of the liver, which they call homogeneous, and it is the initial part. There is another part that becomes white, or the diaphragm, which is referred to as the echo texture of the liver. It has a homogeneous appearance, which is this initial part. This white thing is very strong, Dr. Islam. Could you help me? Is this the diaphragm, or is it something else? Okay. Of course, the signal feels like it's good for me. Is that right? Okay, what is present here is also between the kidney and the liver. Is that clear? This is also the kidney as far as I know. Okay, and there is a part here. You can also feel that the signal in the image is somewhat distorted. Okay? This part at the top. This first one, which is number one, is a homogeneous image, or what is called the echo texture of the ultrasound. This occurs because the ultrasound pulses, as they descend, encounter the hepatocytes, which have a certain size smaller than the wavelength of the ultrasound pulses. Thus, isotropic scattering occurs in this manner, giving you the appearance you see in the received signal. So, this is number one. I call this scattering, with small size or small interfaces that are smaller than the wavelength. This returns the pulses or sends them back to the transducer, which receives them and translates them into its signal. Now, if it encounters rough surfaces in the area below, scattering starts to occur. In this way, in a manner that is such that the signal does not remain as uniform and consistent as it was in the previous scattering. This one I call diffuse reflection. Just a moment, please. I don't want to be too abrupt. When it encounters a surface, it becomes a reflective surface, resulting in reflection that appears as scattered reflection, giving you a signal that resembles this kind of signal. As a result of the interaction between the instant pulse and the reflective surface, if the pulse that is coming down meets a smooth and strong surface, like the diaphragm, reflection occurs, which we all talk about, and this reflection starts to give you a hyper signal in that area. Now, in the part between the kidney and the liver, there is also reflection occurring at that border. The intensity, or what exists there, according to impedance, does not match between the kidney and the liver. So, all of this is present, or every pixel in the image represents a certain intensity. This intensity corresponds to the reflection that occurred, or the type of interaction that took place. The received signal is this. What reaches you is absolutely fine, whether it has interacted with something in any possible way, in a significant manner, like the first area, which is like this area. Reflection may not be homogeneous, or there may be interaction with the liver, or it may occur with something that is smaller in size, resulting in this shape, and it starts to give you this appearance. In any case, your hands show this in a certain way. The first type of reflection that I was talking about is called specular reflection. Here is the incident pulse, and here is the reflected pulse. This occurs on smooth and strong surfaces, like the endocardial or epicardial surfaces, or the valvular or epicardium surfaces. What happens is that the reflection occurs, and you start receiving the specular signal, which is acoustic. Then you encounter a rough surface, which starts to give you the signal that I just showed you a moment ago, where the image is distorted and the signal is not homogeneous, or the reflection is not in one direction like the image above, and I call it what happens, or This is refraction. Refraction occurs when a beam transitions between two mediums, each having a different velocity. For example, you have air and you have water. Air has a certain velocity and water has another velocity. This means that the velocity of the ultrasound beam in water, C1, is less than the velocity in air, C2. C2. No, I'm sorry. It means that when it transitions between two mediums that have differences, what happens is that, for example, here is the wave that is coming to you, and it reaches a certain point between these two mediums. Then, refraction is supposed to occur. It should continue in its path, but instead it experiences this change and starts to move at this angle, which is the refracted angle. This is the incident beam, and this is the incident angle. There is a part that undergoes reflection and a part that undergoes refraction. The refracted angle should be such that if I am transitioning from C1, which is greater than C2, meaning from a medium with a higher velocity to a medium with a lower velocity, then this medium C1, which is the fluid here, is greater than C2. All right, we understand that the medium here, the first medium, had a speed of ultrasound of C1, and the second medium had a speed of C2. If C1 is greater than C2, what will happen is that the refracted beam will move towards the normal. What is the normal? It is the perpendicular to the surface at the interface between the two media. If you transition from C1 to C2 and C1 is greater than C2, what will happen is that it will move closer to the normal. This means that the refracted angle will decrease. When the ultrasound beam moves from a medium with a lower speed to a medium with a higher speed, what essentially happens is that your refracted angle significantly increases and the beam moves away from the normal. The normal is the line at the interface between the two media. For you, when moving from a medium with high speed to a medium with low speed, what will happen is that the speed will decrease and it will move close to the normal for it. The law that expresses this refraction is called Snell's law, which states that the sine of the incident angle is equal to the sine of the refracted angle or transmitted angle, which is equal to the speed in medium 1 divided by the speed in medium 2. That is Snell's law. This shape represents scattering, and this is the refraction that occurs, and this is the attenuation or transmission that happens. It's as if there is reflection occurring or something is being reflected. Also, we mentioned that the beam experiences attenuation. This attenuation is expressed in decibels. The decibel per centimeter per megahertz means how much attenuation the beam loses in decibels for every centimeter of tissue if the frequency is 1 megahertz. This is expressed in attenuation, and we will find that the highest attenuation occurs in bone at 22 decibels per centimeter per megahertz. The attenuation here has increased due to the bone. The attenuation is very high compared to water and other tissues present. So, what does this attenuation depend on? It depends on three things: frequency, depth, and something called the attenuation coefficient. This attenuation coefficient is specific to each material, whether it's bone, soft tissue, water, or anything else. Each has a certain attenuation coefficient or scattering coefficient. Similarly, each material has a specific impedance. If the attenuation coefficient increases for the materials, the attenuation increases. If the frequency increases, the attenuation increases. If the depth increases, meaning you are moving further away, the attenuation also increases. So, I have three factors that modify the attenuation: the attenuation coefficient, the depth you are working with, and the frequency. As we discussed earlier, if your depth increases, you are moving further away. and you will also experience loss. The attenuation coefficient of the material is specific to the material you are working with, whether it's muscle, blood, water, air, bone, liver, or whatever. The highest attenuation I have is found in bone, with its unit being decibels per centimeter per megahertz. Attenuation refers to the original signal that has significantly lost strength. For example, a signal that was originally 100 has reached this interface at a level of 30 due to the effects of reflection, absorption, and whatever else has happened. What has occurred to the signal that reached here at 30? There is an attenuation of 70 due to anything that, as you are aware, displaced the ultrasound pulses and lost all the characteristics of their original beam. This indeed reflects the attenuation. Correct, doctor. Let's stop here. An unclear need is dangerous.